Good morning. Today I am going to explain about the potential due to charged spherical shell. This is one of the important topic in electric potential. So here we have to consider the three situations: when the point is lies outside the shell, when the point is lies on the shell, when the point is lies inside the shell. So that time what will be the potential due to the charged spherical shell? So first of all we have to consider when the point is P lies at a distance of r from the O outside the shell, and this cell is charged shell and whose center is O, and this is at a, the radius of this charged spherically charged shell is capital letter R. Okay, now we have to calculate the potential at a point P. For that purpose, first of all we have to divide this shell into a small strip AB, and we have to calculate the potential due to this small strip AB at a point P. Next you integrate to this that equation, then we will get the potential due to the spherical shell, whole spherical shell at a point P. So for that purpose let us consider a charged spherical shell with center O and radius is R. Radius is R from the O. Let P be any point lies outside the cell, and this point P lies at a distance of R from the O. Just now I told you that is at a distance of R from O. Now cut the shell into small strip of thickness AB and radius is AZ. Now this shell is cut into a small strip AB whose thickness is AB and the radius is AC. Okay. Now we have to consider the angles. AOC is angle theta, AOB is d theta. Now we have to calculate the first thickness of this strip AB, that is can be written as AOB sector, or we can write R into d theta is nothing but a thickness. And next we have to calculate the area of the strip. So here thickness of the strip AB, or from the sector AOB, I can write AB is nothing but a R into d theta, R into angle is d theta. Now the radius of the strip AC, so I can write from the triangle AOC, that is sin theta is nothing but a perpendicular by hypotenuse, that is AC by AO, or AO value is R. So I can write sin theta is equal to AC by R, or AC is equal to R sin theta. So radius of the small strip is can be written as AC is equal to R sin theta, or R is nothing but a OA sin theta. Next we have to calculate the area of the strip. Next after that we have to calculate the charge on this strip. Okay, so area is nothing but a circumference into thickness. Circumference of that small strip is 2 pi r sin theta. Circumference of the circle like that, 2 pi r. Here strip circumference is 2 pi r sin theta into r into d theta. This can be written as A is equal to area is equal to 2 pi r square sin theta d theta. Next, first thickness is over, area is over. Now we have to calculate the charge on this strip. So charge on the strip is, we know that charge is nothing but a density into area. So density value is rho. Area already we calculated, that is 2 pi r square sin theta d theta. So now the electric potential at a point P due to the small strip dV. So now the electric potential at a point P due to the small strip small strip AB can be written as here. We know that the electric potential can be given as charge by distance into 1 by 4 pi epsilon naught. So charge by 4 pi epsilon naught into distances from the strip to point P is x. So that's why AP value is x. So when you substitute the value of this charge, it will be charge value is rho into this one. So here rho into 2 pi r square sin theta into d theta by 4 pi epsilon naught x. Now in this equation we have to calculate the value of sin theta d theta, and let us take this is equation number 1. Now for calculating the sin theta and d theta value, we have to consider the strip, we have to consider the triangle ACP. So according to the Pythagoras formula, I can write AC whole square is equal to AP whole square. is equal to AC square whole square plus CP whole square. So here AC whole square already we know that is r sin theta, and next CP whole square is can be written as from O to at this position capital letter R, and here to here is small letter r. So I can write small letter r minus capital letter R cos theta. This side we have to take. So that's why from the triangle ACP I can write AP whole square is equal to AC square plus CP square. That can be written, AC value already we got, that is r sin theta whole square, plus this can be written as small letter r minus capital letter R cos theta whole square. So this is in the form of A minus B whole square. So and this can be written as here r square sin square theta plus r square, a square is r square plus b square is r square cos square theta, and minus 2ab is minus 2r cos theta. So and this is r square sin square theta, and this is r square cos square theta. So if you take out the r square, it becomes sin square theta plus cos square theta is 1. So here I can write x square is equal to r square plus r square, capital letter R square plus small letter r square minus 2r cos theta. This is only for understanding purpose, no need to write this one. Here we take this equation and integrate, differentiate this equation. When you differentiate this equation, it becomes 2x dx, and differentiation of these two terms is equal to the 0, constant value is 0, 2r sin theta and theta, 2 get cancelled, then x dx is equal to r capital letter R small letter r sin theta d theta. Now we need the value of sin theta d theta. So sin theta d theta value will be equal to x dx by r capital letter R small letter r. So well, substituting the value of sin theta d theta value in equation number 1. So when you substitute the value of sin theta and d theta in equation 1, so this is the equation number 1. Substituting the value of sin theta and d theta value. So x get cancelled, r and r cancel, pi 2. So we got the value dV is the electric potential due to a small strip. Okay, due to the small strip AB at a point P, the value of electric potential rho r dx by 2 epsilon naught r. Now we have to calculate the electric potential due to the whole shell. So for that purpose we have to integrate from the r minus r to capital letter R plus R. So now the electric potential at point P due to the whole shell can be obtained by integrating the second equation from where to where, that is r minus r to r plus r. Then it becomes my r minus r to r plus r integration rho r dx by 2 epsilon naught r. So if you take out the constant rho r by 2 epsilon naught r, it becomes r minus r to r plus r dx or 1 dot dx, and integration of this equation is x into r minus r plus r. Now when you substitute the values of these limits, it becomes r plus r minus r plus r. So minus r minus plus r get cancelled, then we got the value rho r by 2 epsilon naught r 2r, 2 get cancelled, v is equal to rho r square by epsilon naught r. Now we have to calculate the value of rho. So rho is nothing but here total charge on the shell by here total surface area. So here total charge on that will be q, and surface area is, this is the sphere. So area of the sphere is 4 pi r square. So 4 pi capital letter R square. So substituting the value of rho. So when you substitute the value of rho into this equation, it becomes q by 4 pi epsilon q by 4 pi r square into r square by epsilon naught r. So r square get cancelled, then v is equal to q by 4 pi epsilon naught r. So this is the electric potential due to the whole sphere or charged sphere at a point P when the point is lies outside the shell. Now we have to consider the situation when the point is lies inside the on the shell. When the second case is when the point is lies on the shell. So on the shell means we have to consider the situation where small letter and capital letters are equal. Here when the point is lies on the shell, it means capital letter R and small letter r. The distance between O to P we have to consider small letter r, and O to P is already it is capital letter R, radius of the circle, sphere. So that's why small letter r is equal to capital letter R. So the equation will be V is equal to Q by 4 pi epsilon naught capital letter R. This is the electric potential due to the spherical charge, spherical shell on the when the point is lies on the shell. Okay, next situation we have to consider when the point is lies inside the shell. So here inside the shell, now the distance between O to P is R, and here O to capital letter R is the radius of this sphere. So let P be any point inside the shell at your distance of R from O. So that time we know that from the equation number 2, we got the value. We know that from the small strip, the potential at a point, any point, can be given as dV is equal to rho r dx by 2 epsilon naught r. So this is equation number 2. So this by this equation, similar situation we have to consider, that is the shell is divided into a small strip. First of all, we have to consider divided into a small strip. One strip we have to consider, and we have to calculate the thickness of this strip, area of the strip, and the charge on the strip. So next we have to calculate the potential at a point P due to the small strip. Okay, so that value already we calculated. That is nothing but equation number 2. So the potential at a point P due to the whole shell can be obtained by integrating the above equation from the limits or capital letter R minus R to R plus R. So in the first case, we integrate the limits from small r to minus capital letter R to small r plus capital letter R. So now the situation will be reversed. That is capital letter R minus small letter r to capital letter R plus small letter r. So here the limits will be this one, and V is equal to dV. So dV value we have to substitute this one. So when you substitute the value of dV, it becomes r minus r to r plus r rho r dx by 2 epsilon naught r. So here if you take out the constants, it becomes rho r by 2 epsilon naught r minus r to r plus r 1 dot dx, and here this can be written as integration of this one will be x r minus r to r plus x. And next we have to substitute the limits. When you substitute the limits, it becomes capital R minus R, capital R and plus R, capital R minus R will be cancelled. Then we got only plus R, that is 2R small letters. 2 get cancelled, R get cancelled, then becomes rho R by epsilon naught. So again rho value is nothing but a, already we calculated this also, rho is nothing but a charge by total charge by total surface area. So total charge is Q and total surface, and this is the sphere only, so sphere area is 4 pi r square. So substituting this value into this equation, then it becomes Q by 4 pi r square into r by epsilon naught. So next this is V is equal to Q by 4 pi epsilon naught r. So this is equation number 4. This is equation number 5, and this is equation number similar to the equation number 4. Not a similar, it's the same. Here we can consider the cases, that is second case. In the second case, we got V is equal to Q by 4 pi epsilon naught r, and in the last case, third case also, Q by 4 pi epsilon naught r. So from equations 4 and 5, it is clear that the potential on the shell and inside the shell is same. Thank you. For more videos, subscribe my channel Physics.